This instructional video is designed to show a graphical proof of the path independence of entropy, thereby showing that it is a state function. Now, in order to do this, we're going to use the same diagram that we would use for internal energy. So all of these processes are reversible, and each of the red, black, and green paths have their properties listed here. There are a couple of useful results that we'll need to carry forward this proof. And one in particular is that when we have a process that allows us to talk about entropy, we can write out the total differential and if you've watched the video on mathematical proof of path independence, you'll see that this is a total differential that works out to be an exact differential because we have a function of t dt plus a function of v dv. And so entropy is a function of temperature and volume, and it comes out to an exact differential. Another useful result that we'll be using and taking advantage of is that as long as the heat is reversible, we can just use dq over t. And so you'll see this as ds is dq over t for reversible heating. You'll also see delta s as delta q reversible over t. So this is going to be useful. It's going to come back up as one of the multiple ways that we worry about manipulating things when we talk about the entropy. So let's start with path A, which is an isothermal expansion. Isothermal meaning that we don't get a change in temperature. So for path A, what we would argue is that we know what delta Q would be for path A. And that's going to give us nRT 1 ln V2 over V1. And as a consequence of using the dq over t formulation, what we get is that the delta S for path A is nR ln V2 over V1. So this is going to be the result that we want to see. But that gives us the delta S for path A, the black path. So now the green path is separated into two parts. So we want to look at what happens with path B. Path B is an adiabatic expansion. Adiabatic meaning that the delta Q is 0. Well, if delta Q is 0, then your delta S for part B is delta Q over T. And whatever the temperature is, the entire thing is going to be 0. So no contribution on that part. Now for part C of the green path, we can write out our delta S this way, but since it is isochoric, delta V is 0, so integrating from V2 to V2 is just going to give us 0. So the only thing we really need to worry about for our delta S is this integral CV over T dt, and this goes from T2 to T1. So the argument that we're going to use in this case states that we can equate this to a integral that gives us, since there's no V, there's no real work contribution in the internal energy part, and that means that we could then, without doing all of the awful algebra in between, get that this delta S is going to end up being nR ln V2 over V1. And so, since the contribution to the green part from part B is 0, the entire thing comes out to nR ln V2 over V1. So the green and the black results both match. So the last thing we have to do is the red one. So these are a little less forgiving than the green and black paths, but it's okay. So in this case, what we want is for path D, delta S. We're going to need to integrate this thing, and since the temperature and volume both change in this isobaric expansion, what we can do is go ahead and just write that out. So we go from T1 to T3. And in this case, what I'm going to argue is that we will be doing P dV over T. So, integral, our volume goes from V1 to V2, and this is dV over T. So, this piece is pretty familiar, we've got that. This second part, we want to replace P over T using the ideal gas law with nR over V. So, this entire thing gets replaced with nR, V1 to V2, dV over V. That then will be able to integrate pretty straightforwardly. And now we just need to look at part E, because what we're going to do is add all of these up together. So delta S for path E. Well, we can make a lot of the same arguments, but because it's isochoric, our volume doesn't change. So the second part of that will go away. And so what we're left with then is integral as we go from T3 to T1 of CV over T dt. So if we use our calculus and think about this, this integral for part D going from T1 to T3 will cancel this integral from part E going from T3 to T1. And so what we're left with is integrating nR dV over V as we go from V2 to V1. And so the delta S for the entire thing ends up being nR ln V2 over V1. And what we've now found is that we can demonstrate graphically that the change in entropy for the black path, which is all path A, nR ln V2 over V1. For the green path, which is B plus C, gives us nR ln V2 over V1. And for path D plus E, these cancel, leaving only nR ln V2 over V1. As a result, we can safely argue that entropy is indeed path independent and therefore a state function.